I want you to picture something for a second. You're watching a sci-fi movie, maybe it's the Terminator, maybe it's RoboCop, and you see that classic view from, inside the robot's eyes.
Oh, yeah?
That view where there's a red tint to everything, maybe some text scrolling on the side, and these little boxes drawing themselves around people's faces, calculating
Their
distances.
classic machine vision trope.
Yeah.
It is, yeah. It's iconic.
Exactly. And for the longest time, I thought that was just, I don't know, Hollywood magic. Or if it was real, it was some crazy military-grade tech locked away somewhere. But then I started looking at the source material for today's deep dive, this technical guide on OpenCV Python, and I realized, wait a minute, I can do that on my laptop, like today.
You absolutely can.
Yeah.
And you don't need a bunker, and you certainly don't need a cybernetic eye. You just need Python.
That's what we're digging into today. We are exploring OpenCV, specifically the Python wrapper for it. And the mission for this deep dive is, well, it's pretty simple. We want to demystify sight. We want to understand how a machine takes a stream of light, which is what a camera sees, and turns it into data it can actually understand.
And demystify is the right word.
Yeah.
Because when you strip away all the hype, computer vision, it isn't magic. It's math.
Right.
It's just linear algebra wearing a trench coat.
I love that image. So, okay, let's start with the basics. The sources call OpenCV a library, but that feels like a bit of an undersell. This thing has been around for a while, hasn't it?
It has, yeah. OpenCV stands for Open Source Computer Vision Library. It was actually started by Intel way back in the late 90s. They realized that everyone had to write their own code from scratch just to, load a JPEG or find an edge in a photo.
Nobody would ever get to the fun stuff.
Exactly. Nobody would ever get around to building the cool, high-level robotics. So they built the foundation.
And it's written in C++ly, which I know is incredibly fast, but also, let's be honest, it can be a bit painful to write.
It can be heavy, yes. You're managing memory yourself, and that's where the Python wrapper comes in. This is the beauty of what we're looking at. You write in Python, which is readable, it's concise, it's human-friendly, but when you run the code, it's executing those super optimized C++ functions in the background.
So you get the best of both worlds.
It's the classic rapid prototyping benefit. You get the ease of Python with the raw horsepower of C++ly.
Okay, so step one in the guide is installation. And I was expecting a headache here, dependencies, compilers, all that fun stuff, but it's just one command, pip install opencv.python.
It is deceptively simple.
Yeah.
But did you notice what else gets installed when you run that? There's a silent partner involved that's actually key to the whole operation.
I did catch that. NumPy. It installs NumPy.
Exactly.
Now, I know NumPy is the heavy lifter for math in Python for big arrays of numbers, but why are they so joined at the hip? Why can't OpenCV just handle images on its own?
Because to OpenCV, an image isn't a picture. It doesn't know what a cat is or a sunset. When OpenCV loads an image, it immediately converts it into a NumPy array.
So it's just a grid of numbers.
It's just a grid of numbers.
This was the first big, conceptual shift for me reading the sources. We have to stop thinking about pixels as dots of color and start thinking of them as coordinates in a spreadsheet.
That's a perfect analogy. Think of a small photo, maybe 100 pixels wide and 100 pixels tall. In memory, that is a matrix, a grid. 100 columns, 100 rows.
The guide talks about using the jot shape attribute to prove this. You load an image, ask for its shape, and it spits back a tuple, something like 222, 183.
Right, so let's break that down. 222 rows, that's your height. 180 columns, that's your width. But that third number, that 3, that's the most important part for understanding color.
The channels, red, green, and blue.
Well, actually, here is where OpenCV throws a curveball that catches almost every beginner.
Oh.
It's not RGB.
Wait, really? The entire digital world is RGB. Monitors, websites?
Not OpenCV. By default, it reads images as BGR blue, green, red. It's a legacy quirk from how cameras and software were built in the 90s. If you load an image in OpenCV and then try to show it with a different library that expects RGB...
everything looks wrong. The colors are inverted.
Yep. Your reds look blue, your blues look red. So you can think of that 3 as 3 sheets of graph paper stacked on top of each other. The bottom sheet is how much blue is in each pixel. The middle is green, the top is red.
And each little square on that paper has a number between 0 and 255.
Right, because that's the max value you can store in 1 byte of memory. 0 is total black, no light. 255 is full intensity.
So if a pixel at coordinate 50 is 255, 0 in BGR mode.
That pixel is pure, solid blue.
And this is where the fun starts. The guide shows that since it's just a NumPy array, you can just change it
Right.
directly. You just slice the array.
Precisely. You can say, take the region from pixel 0 to 100 and set every single value in there to 0.
And you get an instant black square.
You're doing image editing with algebra. It's incredibly powerful.
Yeah. And you can split the channels apart too, right? With cv2.split.
Yes, you can pull those 3 stacked sheets apart.
Yeah.
So if you're, say, trying to find plants in a drone photo, you might only care about the green channel.
Yeah.
So you split it, you grab just the green matrix and process that. Saves a ton of time.
Okay, so the data structure makes sense. It's a 3D matrix. Let's talk workflow. The hello world of computer vision, reading an image, showing it, and writing it back out.
Sounds basic, but there are important nuances here. You use cd2.imrid to load the file, but you have to tell it how to load it.
With the flags the guide mentioned.
Right. Usually you just pass the file name. But you can pass a 0 as the second argument, and it'll load it directly as grayscale.
Why do that? Why throw away color right away?
Because color is heavy. It's 3 times the data.
Yeah.
3 sheets of paper instead of 1. If you're trying to, I don't know, read text on a page, does it really matter if the letter A is red or blue?
No, I guess not.
Color is often just noise. So loading in grayscale can cut your memory usage and processing time by 2/3 instantly.
Efficiency first. I like it. Now, for viewing, the guide compares cv2.mshow, the built-in window, with using matplotlib. Why bring in a whole separate library just to see a picture?
It depends on where you're working. If you're writing an application like a security camera feed, you use mshow. Pops up a window, it's fast. But if you're a data scientist in a Jupyter notebook, you can't just pop up windows. Matplotlib renders the image right there inside your document. Plus, it gives you axes so you can see the pixel coordinates. Great for debugging.
And speaking of mshow, there was that one weird function the guide said was mandatory, cv2.waitKey0. It sounds like the computer is just taking a break.
It's actually the opposite. Without it, the script finishes so fast the window closes before your monitor can even refresh.
So you'd run the script and nothing would happen.
You might see a flicker, if you're lucky. WaitKey0 freezes the program and says, stop everything and wait indefinitely for any key press. It's the bridge between the machine's speed and our human speed.
It's the pause button. Okay, let's move to something a bit trickier. Bitwise operations. AND or XR not. This felt like a logic class flashback. What's this doing in an image guide?
This is how we combine images in complex shapes. Think about it. If you just paste one image on another, it's always a rectangle.
Right, but real objects aren't rectangles.
Exactly. The example was that OpenCV logo, the one with the weird horseshoe shapes, and putting it on a photo.
On a messy desk, yeah. They wanted it to look like a sticker, not a square patch.
Right, and to do that, you need a stencil. In computer vision, we call it a mask.
Okay, walk me through this again, because the logic is dense.
Okay, so you have the logo on a black background. First, you create a binary mask. You say, anything that isn't black, make it white. Everything else, stay black. Now you have a pure white silhouette of the logo.
The cookie cutter.
Perfect analogy. Now you take that cookie cutter and use a bitwise AND with the desk photo. Wherever the mask is black, it punches a hole in the desk photo. It just turns it black.
So you've got a logo-shaped black hole in your main picture.
Yes. Then you do the reverse for the logo image itself. You keep the colored parts of the logo, but make sure its background is pure black. And then you just add them together.
And because 0 plus the color is just the color, it fits right in.
It fits perfectly. And this idea, masking, is absolutely fundamental. It's used for green screens, for medical imaging, anything where you need to isolate a specific non-rectangular region.
Okay, so that's combining. What about drawing on images? The guide mentions cv2.line, cv2.circle. Aside from making a bad MS Paint clone, why do we need this?
Annotation. Think back to that Terminator vision. When a face detection system finds a face, how does it tell you?
It draws a box around it, a green box.
Exactly. That green box is cv2.rectangle. The text above it that says person, 99%. That's cv2.putText. These drawing functions are the UI of computer vision. They're how the machine talks back to us.
I did like that little detail about the thickness parameter if you set it to -1.
It fills the shape. Yeah, it's a weird little shorthand in OpenCV. -1 means solid.
Now, up to this point, everything's been static. Run the script, see the result. But then we get to interaction, mouse callbacks, and track bars. This is where it felt like building a real app.
This is where we break out of the script mindset and enter what's called an event loop. You can tell OpenCV, hey, listen to the mouse. If the user double-clicks, run this specific function I wrote.
And the example was drawing a circle wherever you click.
Right. And think what's happening there. The window captures the click, gets the XY coordinates, passes them to your function. Your function changes the NumPy array, and the window refreshes, all in milliseconds.
They even built a little paint tool where M switches between drawing modes.
It shows you can build a whole GUI without leaving OpenCV. You don't need a huge separate library if you just need to tune a few parameters.
Which brings us to track bars, the sliders.
Yes. And these are a lifesaver for developers.
Yeah.
Let's say you're trying to find the perfect brightness value to isolate an object.
Right, without a track bar, I'd have to change the number in the code, run it, see if it works, close it, change it again.
Which is agonizing. With a track bar, you just create a slider, you run the program once, and you just drag the bar back and forth in real time until the image looks perfect. It makes your parameters dynamic.
It turns your code into a tool. Okay, let's talk transformations. Resizing seems obvious, but the guide got really specific about something called interpolation.
Ah, yeah. This is a detail that separates the pros from the amateurs. When you shrink an image, you're throwing away data. You have to decide how to summarize 10 pixels into one.
And if you zoom in, you're making up pixels that weren't there.
Exactly. And the default method can look really blocky and pixelated. But if you use something like intercubic, the math looks at the neighboring pixels and fits a smooth curve between them. It generates a gradient. It looks much better, but it's a bit slower.
So intercubic for zooming in, interarea for shrinking. That's the rule of thumb.
That's the rule of thumb.
Then there's rotation. And this isn't just flip 90 degrees. This is rotate 37.5 degrees around a specific point.
Right. And this brings in affine transformations. Sounds scary, but it just means a transformation that keeps parallel lines parallel.
And to do this, we need a matrix, of course.
It's all matrices. You use a function, get rotation matrix 2D to calculate the math for the spin. Then you feed that matrix into another function, warp affine, to actually do it.
So it's like OpenCV splits the planning from the doing.
That's a great way to put it.
Yeah.
You calculate the plan, the matrix, then you can execute that same plan on 100 different images if you want.
Okay, finally, we land on what the guide calls the beginning of segmentation, thresholding.
This is probably the most critical concept for actual analysis. Thresholding is how you separate the signal from the noise.
So in simple terms, it's just converting a grayscale image to pure black and white. No gray at all.
Yes, that's binary thresholding. You pick a value, say 127. If a pixel is brighter than that, it becomes pure white. If it's darker, it becomes pure black.
But why would we want to destroy all that detail? We just talked about fancy interpolation.
Because computers love contrast. Imagine you're building a license plate reader. You don't care about the shadow on the bumper or the dirt. You care about the shape of the letters. Thresholding makes those letters pop out as stark black shapes against a white background. It makes the geometry easy to measure.
It's all about simplification.
It's about making a decision. Is this pixel important? Yes or no?
And the guide mentioned a few other types, like threshtron.
Truncate. Yeah, that means if a pixel is too bright, we just cap it at the threshold. We don't make it white. We just say, you can't be brighter than this. It's good for removing glare without losing all the dark details.
And thresh to 0.
That one says, if you're too dark, you become pure black. But if you're bright enough, you stay exactly as you are. It's like turning off the background lights but keeping a spotlight on your subject.
So looking back at this whole toolkit, we can load images as data, mask them with logic, draw on them, interact with them, warp them, and simplify them to their basic shapes.
That is the OpenCV survival kit right there.
And what strikes me is that none of this is AI in the way we talk about it now. There are no neural networks here, no deep learning.
This is classical computer vision.
Yeah.
And honestly, for many, many problems, this is better. It's faster, it's predictable, it's explainable. If your thresholding doesn't work, you can see exactly why. With a neural net, sometimes you just have no idea.
It's the difference between teaching a kid to recognize a letter versus just tracing its outline.
Exactly. Sometimes tracing is all you need.
Before we wrap up, I want to just throw a thought out there, kind of a synthesis of all this.
Go for it.
We talked about wait key and interaction, the computer waiting for a trigger. We talked about thresholding, recognizing a specific color, like a bright red stop sign. And we talked about geometry rotating and orienting.
I think I see where you're heading with this.
If you chain all those together, isn't that just the brain of a self-driving car? At least the basic version. Wait for input is the camera frame. Threshold is finding the white lane lines. Geometry is figuring out the angle of the curve to steer.
You are absolutely right. The complexity scales up, of course. You have 3D space and rain and pedestrians. But the fundamental building blocks, the atomic units of logic, are exactly what we covered. You find a region, you mask out the noise, you measure an angle, and you take an action.